All right, let's get started. Today's colloquium is by Simon Wing. Simon got his PhD at the Technical University in Eindhoven, the Netherlands. I have to mention this because being Dutch, I have to promote the Netherlands. So we're very excited to have Simon here today. Simon is a principal professional staff scientist at the Johns Hopkins University Applied Physics Laboratory, and he is also an adjunct associate professor at the University of Maryland. Simon does a lot of interesting work, and today he's going to talk to us about untangling drivers of nonlinear systems. Thanks.
Thank you very much. Thank you for having me here. It's an honor. As Alfred mentioned, my topic today is the untangling drivers of nonlinear systems with information theory. So here is the outline of my talk. I will first give a brief introduction to information theory, mutual information, conditional mutual information, and transfer entropy. And then I will discuss two examples of its applications, radiation belt and solar cycle. And then I will end with some concluding remarks. So two variables can be linearly correlated, in which case the standard linear correlational analysis can characterize the relationship. The two variables can be uncorrelated, in which and the distribution may look like a circle of dots. But in a complex system, the two variables may be linearly correlated or may have high order correlations, in which case the standard correlational analysis will be inadequate. But clearly, these distributions this distribution look different than the uncorrelated data. So here, information theory can provide a useful can be a useful tool for characterizing and analyzing this type of data. So suppose that we have two variables, x and y, and the entropy of x is defined as a summation of the p of x times log p of x, where the p of x here is the probability of finding an element of x in the set of x. And the entropy of y is defined in a similar fashions. So the entropy gives a measure of the amount of information in a variable set x. So then, sorry. So then the mutual information mi of x and y is defined as the entropy of x plus entropy of y minus the joint entropy of x and y, where the joint entropy is defined up here. So mutual information is useful to identify nonlinear dependence between two variables. Pictorially, if the blue here is the entropy of x and the red is the entropy of y, the mutual information of x and y is this intersection region. So it's a mutual information of x and y is the information that x and y share. Mutual information of x and y is 0 if x and y are independent of each other. So conditional mutual information, CMI of x and y given z, is shown by this expression here. Basically, CMI of x and y given z determines the mutual information between x and y given that z is known. So if z is unrelated or random, then CMI of x and y given z is just simply mutual information of x and y. And if x or y is known based on z, then CMI of x and y given z is 0. So pictorially, if the blue here is the entropy of x, red is entropy of y, and green is the entropy of z, CMI of x and y given z is this small region right here. So now I'll talk about the transfer entropy. A common method to establish causal relationships between two time series, say x and y, is to use time-shifted correlation function. However, the results may not be clear if x and y have multiple peaks. So here is an example. Say that we have two sinusoidal function, x of t, which is plotted as a blue curve, and y of t, which is plotted as a red curve. So it is possible that x can cause y with a small time delay. But it's also possible that y can cause x with a longer time delay. And one may use the shifted correlation to find out the time delay. So for example, we can calculate correlation of x of t with y of t plus tau, which is the blue curve, which shows a peak with a small tau, with a small time delay. And then we can do the other pair. We can calculate the correlation of x of t plus tau with y of t, and which is plotted in red, and it shows a peak with a longer time delay. But the peak of the blue curve doesn't necessarily mean that x causes y, and likewise the peak of this red curve doesn't necessarily mean that y causes x. So a better alternative is to use transfer entropy, which is shown right here. So transfer entropy, TE of x to y, gives a measure of information transfer from x to y, given that the present or past values of y are known. So TE can be considered a special case of CMI. That is, TE of x of y is just the CMI of y of t plus tau with x of t, given the previous values of y are known. So if no information flow from x to y, then TE of x to y is 0. Unlike correlation, TE of x to y is not necessarily a TE of y to x. So using the same example that I showed earlier, if we know the value of, if we know all the past values of y, that information alone will be sufficient to predict the future value of y, and knowing x will provide little or no information. And so TE then of x to y, which is the blue curve, has little or no peak, unlike the shifted correlations. And likewise, if we know all the past values of x, that would provide enough information to predict the future value of x, and knowing the value of y would provide little or no information, because these two curves are perfectly sinusoidal. And so TE of y to x, which is the red curve, also has no peak, unlike the shifted correlations. So this example here is relevant to the solar cycle study that I will discuss in the second half of the talk, because you can see that all the solar parameters here exhibit cyclical behaviors. But first, I will talk about the radiation belt dynamics. Because I was told that the audience could be mixed. So for those of you who are not magnetospheric physicists, this is just as a reminder, this is the sketch of the magnetosphere. Radiation belts are located in this pink region here, between, depending on the magnetic geomagnetic activity, they are located between 1 and 8 Earth radii. Well, one radius of the Earth is about 6,300 kilometers. So in this region, electrons can have energies that exceed 10 MeV. They are sometimes known as the killer electrons because they can cause serious damages to the satellites. So radiation belt is highly variable, and to a large extent, SolarWind controls the radiation belt variability. But it's not always clear which SolarWind parameters plays the most dominant role. So studies have shown that the SolarWind velocity is correlated with the radiation belt electron flux, GE. So here's an example. An increase in solar wind velocity is followed by increases in the radiation belt electron fluxes at various energies sometime later. And Lee et al. Reported that the solar wind velocity is the most dominant driver. Other studies found that the solar wind density or dynamic pressure are anti-correlated with the radiation belt JE. So here's an example. An increase in radiation in the solar wind dynamic pressure or density is followed by a decrease in the radiation belt JE. And Balikan et al. Reported that the solar wind density controls 78% of the variance of the radiation belt JE with 1 day lag. So here's a plot of the radiation belt electron flux versus solar wind velocity. Two things are worth noting. First, solar wind radiation belt system is nonlinear, so linear correlational analysis will be inadequate. And second, the distribution looks like a triangle, and which was first coined by Reeves et al. Why is there such a huge variability in radiation belt JE when solar wind velocity is low? This problem was first posed by Reeves et al. And in this study, we look at it using information theory. So first, the data set. For the study, we use LANAL geosynchronous satellite observations of the electrons with energy of 1.8 to 3.5 MeV. We use the daily resolutions. And for solar wind, we use the Omni solar wind data at daily and hourly resolution. The merged LANAL and Omni data set have about 6,438 data points. So we first look at the radiation belt JE versus solar wind velocity. These 4 panels show radiation belt JE versus solar wind velocity with 0 day, 1 day, 2 days, and 7 days lag. And the best correlation is found with 2 day lag. That is radiation belt JE of T plus 2 days versus solar wind velocity of T. But it's hard to determine the best correlation just from this scatter plot. So more analysis is needed. So the top panel here shows the shifted correlation, correlation of JE of T plus tau with solar wind velocity of T. And it shows that there is a peak at tau equals 2 days. But because the system is nonlinear, we need to do more than just the linear correlations. So here we repeat the analysis with mutual information, which is shown in blue, and transfer entropy, which is shown in yellows. So the yellow line shows the transfer entropy from solar wind velocity to radiation belt JE. And it shows that the transfer of information from solar wind velocity to JE peaks at also at tau equals 2 days. So next we look at the radiation belt JE versus solar wind density in similar format. Radiation belt JE anti-correlates with solar wind density. And the anti-correlation has a minimum with tau at tau equals 1 day. And the transfer of information from solar wind density to JE peaks at tau equals 1 day. But what is interesting is that solar wind density anti-correlates with solar wind velocity. And the transfer of information from solar wind velocity to density peaks at tau equals 1 day. So this is the summary of the observations. Radiation belt electron flux correlates with solar wind velocity with a 2 day lags. Radiation belt electron flux anti-correlates with solar wind density with a 1 day lag. But solar wind density anti-correlates with solar wind velocity with a 1 day lag. So given these solar wind properties, if this is true, could this just be a coincidence? Conversely, given this solar wind velocity, if this is true, could this just be a coincidence? But is it possible that solar wind velocity and solar wind density each exert influence on the radiation belt independently? And if so, how can we separate the effects of the solar wind velocity from density and vice versa. So in this study, then we use CMI, conditional mutual information, to separate the effect of solar wind velocity from density and vice versa. So the top left panel plots the JE of T plus tau with solar wind density of T given solar wind velocity. And it shows that there is a peak at tau equals 0 that can be contrasted with the TE plot that I showed earlier, which shows a peak at tau equals 1 day. So removing the effect of the solar wind density shifts the peak, the lag times from 1 day to a 0 day. So let's look at the velocity effect. So this plots the CMI of JE of T plus tau with velocity of T given solar wind density of T. And it shows a broad peak at tau equals 2 to 3 days. And that can be compared with the TE plot that I showed earlier, which shows a narrow peak at tau equals 2 days. So removing the effect of solar wind density basically lower the peaks and broadens it. Basically, it removes some of the information from tau equals 1 and 2 days that correspond to this density peak. So the effect of the solar wind density has been previously attributed to the magnetopause shadowing, that is an increase in the solar wind density or solar wind dynamic pressure. The two parameters tend to track each other, would compress the magnetosphere, which would cause some of the radiation belt electrons to escape to the solar wind. And then the compression also launches ULF waves that can distribute the losses radially. So what we have shown here is that this process is fast, is immediate. The response time is less than 24 hours, which is faster than we would have gotten if we had just used if we had just used the correlational analysis or the transfer entropy, in which case in both cases the peak is at tau equals 1 day. But after subtracting the effect of the solar wind velocity, it turns out that the effect is less than 24 hours, it's 0 day. Okay, so the effect of the solar wind velocity has been attributed to a few or several mechanisms. I list 2 of them right here. It can be caused by the electron acceleration, caused by the ULF waves generated at the magnetopause by Kelvin-Helmholtz instability. Another mechanism that has been proposed is the local acceleration caused by the VLF waves during particle injections. But what we have done here is to show that the true effect of the solar wind velocity is 2 to 3 days, which is really the same as what we would have gotten from the correlational analysis. But what we have shown here is that these 2 days is not aliasing of the anti-correlation between solar wind density and velocity with 1 day lag and solar wind and radiation belt JE with solar wind density with 1 day lag. So so we eliminate the possibility by doing this analysis. So we could perform the same analysis for other solar wind parameters, and we can rank the solar wind parameters based on the information transfer to radiation belt JE given solar wind velocity. So at the very top is the solar wind velocity, followed by the magnitude of IMF, solar wind dynamic pressure, solar wind density, and so forth. So now we look at the triangle distributions. The plot of the radiation belt electron flux versus solar wind velocity looks like a triangle, so it's called triangle distribution by Jeff Reeves et al. And there is this huge JE variation when solar wind velocity is low. Well, so this is the triangle distribution again. So it turns out that the triangle distribution is well ordered by TE. So if we bin the data and then calculate the transfer entropy in each bin, and we can see that the transfer entropy of the solar wind velocity to JE with t plus 2 days is well ordered. High JE corresponds to high TE and low and vice versa. And then we can look at the solar wind density effect on the triangle distribution. So this plots the JE of t plus 2 days versus solar wind velocity of t versus solar wind density of t. So both solar wind parameters. So the JE lags 2 days by these two solar wind parameters. And there is the density. The color here is density. Velocity is the x-axis, and y-axis is JE. So there is a density gradient in the x direction because solar wind velocity and solar wind density anti-correlates. But we recall that from our analysis that I showed earlier that the response of the radiation belt JE to solar wind density is very fast, less than 24 hours. So using the information, then we plot the JE of t plus 2 days versus solar wind velocity of t versus the solar wind density of t plus 2 days, so that there is no lag between solar wind density and JE. And so now we can see density gradient in both x and y directions. When solar wind velocity is low, high solar wind density or high solar wind dynamic pressure corresponds to low JE and vice versa. So this is the magneto-pulse shadowing effect that I discussed earlier. So then I'll move on to the next topic, which is how we can improve modeling with information theory. The information theory can help select input parameters of a model. So here's an example. So this shows the solar wind parameters, the ranking of the solar wind parameters based on the information transfer from to radiation belt JE. So if we were to develop a model that predicts radiation belt JE, we may want to consider the input parameters that are highly ranked. So we can use this table to select what input parameters to choose. And another way to improve modeling is to detect non-stationarity in the system dynamics. So solar wind radiation belt system dynamic is not stationary. And so here I show that I calculate the running sliding window of TE of solar wind velocity with JE of t plus 2 days. And I plot this window TE for the first 2,500 days since January 1st, 1989. So it shows that the dynamic is not stationary. There are periods when the TEs are high, and there are periods when TEs are low. So if we were to develop the radiation belt model, we may want to consider that, or take into account that this non-stationarity in the solar wind radiation belt system. And then the information theory can provide the prediction horizon. Prediction horizon refers to how far ahead can one predict a variable. So for example, if we use solar wind density to predict radiation belt JE, the prediction horizon will be about 2 days, because after 2 days, the information is at the noise level. I think I might have forgotten to mention that this solid green line or green curve is the noise, and then the green dotted lines are 3 sigma above the noise. So we consider that anything above 3 sigma may be significant. So anything below 3 sigma will be considered noise. If we use solar wind velocity to predict radiation belt JE, the prediction horizon will be about 7 to 10 days, and after that will be in the noise level. And this is just aliasing because the solar rotation is about 28 days, and the solar wind velocity repeats or tends to correlate it 28 days later. All right, so here are some of the important points. Solar wind velocity is the most dominant driver of radiation belt JE. The relationship between solar wind density and velocity and JE is complicated, partly coincidental and partly causal. And what we have done here is to use information theory to untangle the two important drivers. RBJE response to solar wind density has 0-day or less than 24-hour lag instead of 1-day lag obtained from correlational analysis. Radiation belt JE response to solar wind velocity has a lag of 2 to 3 days. What we have done here is to show that this 2 to 3 day lag is no aliasing of anti-correlation between solar wind density and velocity with 1-day lag, and then radiation belt JE with solar wind density with 1-day lag. Then we look at the triangle distribution. High solar wind solar wind velocity, there is high transfer entropy and strong causal control. For low solar wind velocity, the density or pressure appears to play an important role. And then the TE and CMI can be used effectively to improve modeling by selecting model input parameters, detecting changes in the dynamics of the system, and determining the prediction horizon. Okay, so next I will talk about the solar cycle dynamics. The roles of the solar parameters in the solar cycle dynamo are not fully understood. It is still, for example, it is still a challenge to predict sunspot number. This shows the model predictions of sunspot number at the solar max for the solar cycle 24. It shows a very wide range of prediction from 40 to 190. The observation shows it's about 80, and the mean prediction is, I think, it's about 110. So for the study, we apply information theory to identify causal parameters in solar cycle and the response lag times. We hope to provide observational constraints to solar cycle models and theories such as surface flux transport models, flux transport dynamo models. Just as a reminder, because many of you in the audience are experts on this, in the Babcock-Lighton type model, we start, say, at the solar minimum. The poloidal field in the polar region is affected downward to the base of the convective zone by the meridional flow, and from there, meridional flow carries it towards the lower latitudes. As it does so, the differential rotations shear the magnetic field, leading to the growth of the toroidal fields. And the shearing motions would twist and turn the magnetic field, creating regions of a strong magnetic field, which are buoyant. And the buoyancy force pushes or moves the fluxes, the toroidal fields, to the photospheres, where they appear as the pairs of active regions or sunspots with a tilt. And then as the sunspots decay, they move poleward and leading to the growth of the poloidal field, and then the cycle begins again. So the important parameters in the Babcock-Lighton type model is the meridional flow, polar field, and flux emergence. So for this study, we assemble a lot of data sets, sunspot number from the Belgium website, sunspot area from a NASA website, meridional flow from Roger Ulrich at UCLA, polar faculae from Munoz Jaramillo, polar field and axial dipole field strength from Yiming Wang, AA index from a NOAA website. All data are evaluated at the monthly resolution. So this shows the solar parameters used in our study. The blue curve shows the normalized sunspot number, and the red curves shows the AA index, polar faculae, polar field strength, so axial dipole field strength, and the meridional flow. So all the solar parameters exhibit these solar cycle variations. So we look at first the the relationship between sunspot number and AA index. The solid curve here shows the AA index, and then the dashed curve shows the sunspot number. Both curves exhibit cyclical variations. So in the study of the magnetosphere, it is well known that sunspot number can affect the geomagnetic activity and hence the AA index. However, Hathaway et al. Show that the minimum of the AA index is correlated with the maximum of the sunspot number of the next cycle. So for example, if the minimum AA index is low, then the maximum sunspot number of the next cycle is also low. And when the minimum is high, then the next cycle sunspot number maximum is also high. So the studies suggested that the low-level geomagnetic activity is correlated with the IMF, which is related to the polar field. So we look at this sunspot number AA index relationship with the information theory. So the left panel here shows the shifted correlations, correlation of AA index of T with sunspot number of T plus tau, which is shown in blue, and then correlation of SSN of T with AA index of T plus tau, which is shown in red. So the peaks of the red and blue curve are very similar. However, we get a different story from transfer entropy. So the blue curve here shows the TE of AA index to sunspot number, and the red curve shows the TE of sunspot number to AA index. So it shows that there's more information transfer from sunspot number to AA index. The red curves are higher than the blue curves. This information cannot be obtained from the correlational analysis. So it shows an example of the power of our methodology. So next we look at the relationship between sunspot number and the polar field in the same format. The shifted correlation between polar field and sunspot number shows a peak at about 65, at lag times of 65 months. But we get a different picture from the transfer entropy. The blue curve shows the TE of polar field to sunspot number, and the red curve shows the TE of sunspot number to polar field. And so it shows that the information transfer from the polar field to sunspot number peaks at tau equals 30 to 40 months, not 66 months as assumed in some models. And so we need to, it's not clear what causes this peak. Perhaps that the poloidal field submerges at the lower latitudes, or the toroidal field emerges at higher latitudes. But more study is needed to determine this. And the peak here is significant. It is about 19 sigma away from the noise. It's also interesting to see that there is significant information transfer from sunspot number to the polar field, which is the next topic. So which parameters control the polar field? In the surface flux transport models and flux transport dynamo models, the meridional flows can determine the strength of the polar field. But in the recent model by Upton and Hathaway, the amount of flux emergence, which can be proxied by sunspot number, can also determine the polar field. So we look at these two parameters with information theory. The blue curve shows the meridional flow, TE of meridional flow to polar field, and the red curve shows the TE of sunspot number to polar field. So it turns out that both parameters transfer information to the polar field. However, each parameter dominates over the other at different lag times. So at lag times of 30 to 40 months, meridional flow transfers more information to polar field than the flux emergent or sunspot number. But at lag times about 50 to 80 months, it's the other way around. And then at lag times 90 to 110 months, the meridional flow transfers more information to the polar field than sunspot number again. And this peak at 30 to 40 months here is positive correlations, which has implication to the meridional flow profile. In Dikpati et al. Model, the positive correlation between meridional flow and polar field can be attributed to the meridional flow profile that peaks at mid-latitudes. So what our results here suggest that the meridional flow profile perhaps peaks at mid-latitude. And this is actually observed in Ulrich et al. Study and Upton study as well. So Scheele suggested that polar faculae can be used as a proxy for the polar field. So in this study, then we determine how good of a proxy the polar faculae are in the context of the solar cycle dynamo. So the top panels here shows the, on the left shows the shifted correlations between the polar field and sunspot number. On the right, the blue curve shows the TE of polar field to sunspot number, and the red curve shows the sunspot number to polar field. Actually, these two figures have been shown previously, like 2 or 3 slides ago. The middle panels show the same thing, but for the polar faculae. And the bottom panel shows axial dipole field strength, which has been suggested by Yiming Wang as an even more fundamental parameter to solar cycle dynamo than polar field. So we can see that there are some similarities and differences between among these 3 parameters. But overall, polar faculae curves is very similar to polar field. For example, the transfer of information from polar field to sunspot number peaks at tau equals 30 to 40 months, and it's 30 months for the polar faculae, and the peak significance is 19 sigma for the polar field, and it's 23 sigma for the polar faculae. And why are we doing this? Well, polar faculae data are available since 1906, whereas polar field data are available only since 1967. So to study the long-term effects of the polar field, polar faculae can be useful. So here is an example. Dikpati et al. Suggested that the meridional flow is slower at the bottom of the convective zone, and hence the polar fields from the last 3 solar cycles should affect the sunspot number. So we plot here the TE of polar faculae to sunspot number, and it shows that it peaks at 30 to 40 months, which is what we have obtained before with the polar field, but it persists at a lower level thereafter for at least 400 months, or about 3 solar cycles. And so what is also interesting is that there are minima at about 1 and 2 solar cycle periods. So next we compare the information transfer from the polar field, polar faculae, and meridional flow to sunspot number. The blue curve shows the TE of polar faculae to sunspot number. Purple curve shows the TE of polar field to sunspot number, and the brown curve shows the meridional flow to sunspot number. And the plots are noisy because the data have shorter time span, limited by the availability of the meridional flow data. So it shows that the TE of polar faculae or polar field to sunspot number dominates over the meridional flow, and this may be consistent with the Dikpati model. But what we show here is that this dominance occurs at about tau equals 30 to 40 months. And then at about 120 months, the meridional flow transfers more information to the polar field than the sunspot number. So in summary, TE of SSN to AA index is greater than TE of AA index to sunspot number, which probably is expected, but we show this rather nicely with the information theory. TE of a polar field to SSN peaks at about 30 to 40 months. So the response of SSN to polar fields peaks at about 3 to 4 years, not 5.5 years. Polar faculae transfers similar amount of information as the polar field to SSN, confirming that polar faculae is a good proxy for polar field in the context of the solar cycle dynamics. TE polar field to sunspot number is greater than the TE of meridional flow to sunspot number at tau equals 30 to 40 months. And TE of meridional flow to polar field peaks at about 30 months and 90 to 110 months, whereas from SSN to polar field, it peaks at 50 to 80 months. TE of polar faculae to SSN peaks at 30 to 40 months, but persists at a lower level for at least 3 solar cycles. Our results provide observational constraints to solar cycle models and theories. More work needs to be done to understand our results, and we are interested to try other models or parameters. Thank you very much.
Thank you, Simon. We have plenty of time for questions. I'm sure there's questions. Nope. All right, Mary.
There's different types of high solar wind velocities, whether it's a low mass ejection or high speed streams, and they have very different effects on the radiation belt. So in one case, you have a fast effect from the seeing shots, and then in the other case, you have an integrated over longer time effect from the high speed streams. And I think it would be interesting to apply these types of techniques to separate those two types as opposed to you're combining the two.
Yeah, I think that's an interesting point. And yeah, this is just our first entry into the radiation belt, but there's a lot of things that we can do more. Yeah, thanks. Yes.
Ricky?
Yeah, the analysis of the polar faculae sunspot number, the one where you go over the longest time lags. At what point do you run out of data?
Yeah.
Use this analysis? I notice your noise curve, which I don't understand how it's calculated.
Yeah.
It's always constant. And you talked about things like prediction horizon, but I mean, when you've only got order 20 solar cycles to look at, even less than that, like polar faculae data, how confident can you be that you can look out that far?
Yeah, so I stop here at about 400 months. I have actually tried extending it to larger lag times. But when you do that, like you say, then you start running into a data insufficient problem because then this curve, the blue curves, then will start getting noisier because we only have polar faculae data, say, over about 10 solar cycles. So if you try to determine the lag times, they are larger than 3 or 4 or 5. As soon you start running out of data points. So this curve, the blue curve, then will start getting noisier. So that's why I stop here. As to your second question, which is about the noise, so we calculate noise from the surrogate data. I don't know if you're familiar with that. So we randomly permutate in this case, we randomly permutate the polar faculae data and then apply the transfer entropy. And we do that, I think in this case, I don't remember, maybe 1,000 times, and then calculate the mean noise and then the standard deviation. So this dotted line here is the 3 sigma away from the noise. And so this peak here, I don't remember, but it's 20 or some sigma away. So they're quite significant.
Correct me if I'm wrong, but in that calculation of the noise, you make an implicit assumption about the type of noise that you have. Is that correct?
So here we assume that what would happen if the signal is just random, right? And the reason, but we don't just generate number randomly. We permutate the index of the input array. That way, the noise still maintains the characteristics of the input signal. So, for example, it still has the same amplitudes and so on.
Yeah, but if you were to look at the power spectrum of your permutated signal, it looks very different from the original signal, right? Because you've distributed the power.
Yeah. So it is. So that's right. Yeah. So that's because we are saying here is that if the signal, what happens to the TE if the inputs are just random? So that's what we are. That's the null hypothesis that we're after.
So if we were to look at non-linearity, then we would make sure that the autocorrelation of the surrogates is the same as that. Right.
Yeah.
Right. So we've done that in some cases.
Yeah.
Okay.
Yeah. Okay.
Other questions? I do have maybe a dumb question. So in this case, you're showing that the red curve is above the blue curve for every time lag. Does that imply some sort of causality, or can you derive some kind of extra knowledge for what causes what out of that?
Yeah. So these curves here, which is the TE of SSN to polar field. So it's significant. So it suggests that there is Upton and Hathaway suggested that the flux emergence can be causally related to the polar field, and sunspot number can be used as a proxy for the flux emergence. So in their model, they show that the flux emergence can which are really the seed populations of the polar field. So the more seeds you have, the more sunspot numbers, then the stronger the polar field becomes. I think maybe Lisa may say more about that. She's an expert on this.
Yeah, generally the asymmetry is considered.
Okay.
Yeah.
So how then do you interpret a case like the other one you showed, where the one curve is above the other first, and for a different time lag they reverse?
Yeah,
And how do you interpret that physically, I guess, is my question.
So I think that so this is my first entry into the solar physics here, but I think that physically it's just a different response times from different parameters, right? So from a polar field.
Feedback loop, so one influences the other and the other.
I think you're talking about in case like maybe this. What is it? Like here, for example, you have peaks here, and then the other parameter peaks here, so there's a reverse. So it's just so to me it seems like it's just a response time due to different parameters, and maybe there is some feedback involved, but I'm not sure. I mean, yeah, we see that as well in this plot here.
That was the one I was thinking of. Yeah.
Yeah. Right. So it's just I don't know. Simplistically, I think this is just the response times due to different parameters. But maybe the modelers can tell me I'm wrong. Yeah.
Ricky?
So the TE statistic you talked about in a relative sense, do you have any meaning in an absolute sense? I see you're bounded by one most of the time. Is one something special?
No. It's so TE just the information transfer, and so if it is 0, then we know there is no information transfer. But the magnitude of it, depends on the problem set or on the variable, the set of variable, right? So if you have a variable that can assume a lot of states, then you have higher information content in that variable. On the other hand, if you have a variable that can only go 0 and 1, so that would have a low information content. So that's the information content.
So you didn't precondition the data? You're looking at various different types of data. You're not preconditioning to normalize the unit variance or anything like that?
I don't remember, but I think that even if I normalize it, I still get the same. Normalizing it will not change the information content, right? I mean, you just simply scale it. If the curve, so say if you have 0 and 1, and then you can have 0 and 100, you know, and you still get the same information content, right? You just simply scale the amplitudes. That's right, yeah.
Anybody else? Nope. Okay. Well,
There's one question.
another question? Is there a question?
No.
Nope.
Okay.
Okay. All right. Let's thank Simon again. And Simon, you'll be around the rest of the day and sometime tomorrow.
I'll be around for the rest of the day. I'm not sure if I'm needed, I can come back tomorrow. But I have a plane to catch at noon.
Okay.
Yeah.
All right.
Okay.